Okay, so we developed this modified Newtonian theory for a reason. I'm going to go ahead and tell you that for blunt bodies, so blunt, modified Newtonian theory, I'm just going to call this MNT, is actually fairly accurate. But what about if I have thin bodies? I mean, we developed part of it using this flat plate. And so, how about here? Is it accurate in this case? Well, the great thing is we can actually figure that out perfectly. We can figure out exactly how close it is on everything it needs to do. So let's look at the difference between modified Newtonian theory for a flat plate and our exact shock expansion theory. Okay, so we've done this in the past. I'm not going to bother to do it now, but if I have a flat plate, and let's see, I'm going to put this at a Mach 8. I have magical powers, I can do that. I can just put it at Mach 8 if I want to. And it's at 15-degree angle of attack. I'm going to have a shock wave on the bottom. I'm going to have an expansion fan on the top, and all is well. Shock wave right here, expansion fan right here. So from the past, I can go through and I can calculate everything. Now, we've done that a bunch, so I am going to just steal that for the moment and just give you what the coefficient of lift and coefficient of drag would be. Just know that we would be finding what P2 is right here. We would find P3 right here. And using our angle of attack, which is 15 degrees, we could then figure out the rest. So just know that's where it's coming from. I'm not going to be going through all that right now. So in the end, what I get is that my coefficient of lift per unit span is going to be equal to 0.2032. And my coefficient of drag is going to be equal to 0.0545. Okay, so this right here is exact, it is perfect, it is exactly what's going to happen for a supersonic flow at Mach 8. So now we got to say, okay, we've got that, but is modified Newtonian theory going to give me the same answer? So let's find out. So modified Newtonian theory is going to give me something, well, let me set up slightly differently. So in here, I did define this with P3 and P2. I'm going to change that just so I have the same as your textbook. Make sure I'm doing this very, very similar. P2, P3. Okay, there you go. So I have that 15-degree angle of attack. And for modified Newtonian theory, I don't have any Mach number in there. It doesn't even bring up Mach number. I don't even have to worry about that. And we're actually just going to simplify this, make it Newtonian theory, just make it even easier myself. Let's make things nice. Okay, so for Newtonian theory, my coefficient of pressure on the bottom, that is going to be equal to, call it CP3, and that will be equal to 2 sine squared of alpha, which is equal to 2 sine squared of 15 degrees. And that's equal to 0.134. Okay, first off, you are probably noticing there's a difference here. But don't worry, that's a coefficient of pressure, not coefficient of lift. I'm jumping ahead of myself. My goodness. Why do I do that? Okay, now what's the coefficient of pressure on the top? Well, that's not too hard to find, because remember that our coefficient of pressure equation is equal to P minus P infinity over stuff. And with Newtonian theory, in this section, this will be equal to P infinity minus P infinity over stuff, which is 0 divided by stuff, and 0 divided by stuff is simply equal to 0. So I have 0 on the top, I have 0.134 on the bottom, and using that I can then get my coefficient of lift and my coefficient of drag pretty simply. So coefficient of lift, you're simply going to be equal to CP3 minus CP2, and that's going to be times cosine of alpha. So it's equal to 0.134 cosine of alpha. which is equal to 0.1294. And my coefficient of drag is going to be equal to CP3. Looks like another C. It's a horrible parentheses. There you go. CP3 minus CP2. And it's going to be sine of alpha this time. We're just doing the opposite component. That's going to be 0.134 sine of alpha, sine of 15 degrees. Don't know why I plugged in alpha, just said alpha both times. That's going to be equal to 0.03468. Okay, looking there, we can already see that they are quite different than my earlier results. Not the same. Not the same at all. As a note, as I get to higher and higher speeds, this will be better and better approximated by Newtonian theory. But I'm not there yet. So it doesn't do a very good job. Now, one thing that might surprise you, though, is that lift over drag exact and lift over drag Newtonian theory are exactly identical. But why? Why, when my coefficient of lift and my coefficient of drag are off, is my lift over drag, that ratio, exactly equal at whatever angle of attack we choose? The answer is just definitions. It's really, don't let this confuse you. It's nothing special here. This is not special. That's just from trig. Because remember, like lift and drag are always coming from this normal force right here. In, that's drag, that's lift. I have some angle right here, which is the angle of attack. And so lift over drag is simply equal to, normal force cosine of alpha over normal force sine of alpha. And what you'll notice here is that the normal force cancels, and so all it matters on is the angle of attack. So that is why they're the same. It's just because it's based on geometry. Don't overthink that one aspect of it and be like, oh, well, this is magic. It works every single time. It does, but just because geometry says it should, not because there's anything absolutely amazingly special about it. Okay, so long story short, blunt bodies, this works great. Flat plates, very thin bodies at small angles of attack, not the best until you get to very, very high Mach numbers. But for blunt bodies, works pretty good. And that's it for this.